Welcome back to Astronomy 110, everyone. What you're looking at here in figure 2.9, which begins section 2.2 about ancient astronomy, is a set of images of the moon during a lunar eclipse. And in fact, it's not an artificial editing of these images, but natural effects that cause the moon to, during eclipse, become red and then emerge into white light reflected. Again, this is a set of images of the moon during eclipse that introduces our section about ancient astronomy. So, Earth civilizations have for thousands of years history been trying to understand the night sky. Many ancient societies had a yearly calendar. Babylonian, Syrian, Chinese, Egyptian, Mayan, European, etc. So a yearly calendar naturally is the duration of time that it takes Earth to go around the sun, which wasn't a given, accepted fact over our thousands of years of history. But in fact, people did have yearly calendars. For example, Polynesians could travel the largest oceans by stellar navigation, understanding the positions of the stars over the course of the year. And expectations of a round Earth and moon is thousands of years old. Even though the geocentric Earth-centered model persisted for hundreds and thousands of years, the expectations of a round Earth is an old idea, and one of the oldest and most easily visible pieces of evidence of this is the Earth's round shadow on the moon during a lunar eclipse. But if you travel great distances, another piece of evidence is that some stars will pass below the horizon and out of field of view, just like when a ship sails away in the distance, eventually its parts go out of field of view as it sails very far away. So there is a mixture of correct and incorrect ideas over the course of astronomical history and human history. And many of these ideas might have been correct, but they couldn't distinguish, they couldn't conclude that the sun, not the Earth, that the sun was the center of the solar system. Basically, a strong reason for that is because it came to a disbelief that the closest stars could be so unbelievably profoundly far away. So they thought that if Earth was going around the sun and the dots in the sky were other stars in the universe, they expected that as Earth went around the sun, that they should see a parallax motion of the stars as Earth orbited the sun. But they didn't observe one. So instead, it was expected that the Earth must have been the center of the universe, and that persisted for thousands of years. So the parallax motion actually is there, but it's so small that the human eye could not perceive it. It's so small because the stars are so far away. So some things could be done and perceived and measured correctly, like calculating the circumference of the Earth, but many others not. So take a look at this picture here. By this geometry, we can see that the farther away the sun is, the closest to perfectly parallel are sun rays that reach the Earth. So here's the Earth, here's the direction of the sun. And if we imagine something at location A or location B or location C, we can see that these rays of light, if they were coming from a light source, get closer and closer to parallel. So if this object were farther and farther and farther away, such as the distance to the sun, eventually these light rays would look parallel as they do when they come from the sun. So sunlight leaves its source and travels through empty space and reaches the Earth, and those light rays create shadows on Earth. And by measuring and comparing the angle made, as depicted in this diagram, made by the shadow of some object like a pole or a stick, here it's characterizing a column. There's a column in Alexandria of Egypt. And the shadow that it makes creates an angle with the direction of the sunlight. Here's the sunlight coming and reaching the surface of the Earth, here is some source of a shadow, such as a column or a stick or a pole, and the shadow is tilted. But for many latitudes, on a day like summer solstice, when the sun is directly overhead, the sunlight does not create a shadow. And if the if the Earth were to be flat, these angles would be the same. The angle that the shadow makes with the source of blocking the sun, like this pole here or a pole here. There's a wall and Serene, two different locations on Earth. If the Earth were flat and the sun were directly overhead, they would make the same shadow. No shadow, basically. But if the Earth is curved, then this angle that the shadow is cast at is determined by the curvature and thus the size of Earth. So, given that the Earth is not flat, the angle is different, as long as the measurements are made from different locations on a spherical object. And Eratosthenes made this measurement thousands of years ago, and it's accurate to today's measurements within 1%. So that's a pretty impressive measurement to be correct about for thousands of years, but still, it wasn't concluded that the Earth is round and it travels around the sun. So actually this measurement is pretty accessible, and you too can make this measurement on a summer solstice day. And with some geometry, a few formulas, certainly a pole, a pen, and a calculator, it's pretty easy to make this measurement, this calculation, within a few percent of the accepted value. If you want some hints for how to do this, please join me for office hours, certainly. But I guess the extra pieces of equipment that you'll need, in fact, are shadows and the sunlight and a solar system in which you have an Earth going around the sun. And this wasn't the only startlingly careful prediction that is thousands of years old. Another is that the Earth's spin axis, so here is a picture of the Earth, this is a picture of a little top, or the Earth spinning on its axis is like a top. The Earth spinning on its spin axis generates the geometry of a north and a south spin axis, or a pole, that points to a direction in the sky. And at this point in Earth's history, it points to approximately the star Polaris. But actually, thousands of years ago, they were able to predict that this direction of the Earth's spin axis changes over thousands of years, over 26,000 years. And that was achieved over 2,000 years ago in what is present-day Turkey by Hipparchus, who devised a sky coordinate system and brightness scale that's still used today called the magnitude scale, but he was actually able to determine that the Earth's spin axis wobbles on its axis over very long time scales. So if you happen to be able to live for thousands of years, you would be able to witness yourself that the pointing of the spin axis changes over time. And although the north pole of Earth's spin axis nearly perfectly points toward the star Polaris, it used to be different, and in fact, Hipparchus was able to calculate how fast it changes. And the change of this direction of the Earth's spin axis is called precession, and it occurs because Earth is not a perfect sphere. In fact, it is slightly flattened. Its bulge at the equator is wider than the north pole to south pole distance. So this bulge at the equator causes the moon to pull on the Earth in an uneven fashion. So both the moon and the sun pull on this bulge at the Earth's equator, and it causes the Earth to wobble like a top. And this wobble is actually the reason why there is a mismatch between traditional astrological constellations that you read in the newspaper that are associated with a birthday and the location of the sun on the same person's birthday. So you can look in the newspaper what your quote-unquote horoscope is, but in fact that's not the constellation that's behind the sun on your birthday. And usually it's offset by about one astronomical constellation. So, with so many successes, you might wonder, well, why didn't the ancients get it all correct? And it really came down to two deep-seated biases that required indisputable observation by the successes of the first telescopes used to study the sky. And these deep-seated biases were an inability to believe that space could be as big as we find it today, and that the circle is the perfect shape that explains all motions. So the ancients believed that they needed circles to explain any orbit, whether it was the orbit of a planet going around Earth or the orbit of a planet going around the sun. So there was a belief that the circle is a perfect shape and can explain all motions. And those beliefs made understanding retrograde motion, demonstrated here, very complicated. They had to use ideas like an epicycle, that planets moved on circles upon circles, epicycles on top of main circular orbits that were very complicated. They had to use over 80 circles, over 80 epicycles, and still not be able to explain the observed retrograde motion of Mars. So here in this diagram you see the bird's eye view of the Earth going around the sun and the moon going, Mars or another planet's orbit also around the sun. And here on the right hand side we see what we see in the night sky. So if we are looking from Earth and we are looking at this object here with a yellow dot, how does it look in the sky? And that's what is depicted here, the nighttime stars and the motion, or the apparent motion, of that outer planet. So here we can see what it looks like in the heliocentric view, but in the past people used to believe that the Earth was the center of the universe and everything orbited the Earth, and so they had to try very hard and incorrectly to explain this observed retrograde motion using circular orbits. But we find that if we use a sun-centered orbit, it's actually quite easy to explain retrograde motion, really as simply as understanding why the local train on the subway appears to go backwards when it stops at a local stop if you're watching it from the express train. So if you're on the express train and you happen to see the local train beside you, and you're both going forward, you're both going wherever, in the same direction, and a local stop approaches, and so the local train starts to slow down. However, it's still going forward. It's not going backwards. It's going forwards, but it's slowing down, and relative to you, it appears to go backwards. And that's what's happening here. The orbits of an inner planet are quicker than the orbits of an outer planet. So the letters label coincidental times of the locations of these different planets. So E, this inner planet Earth, is here, and the outer planet is at position E here. So if we look from Earth, we see the planet at position A at a given time, located here relative to the background stars. And then some time passes and Earth is at B, and the outer planet here has also traveled in its orbit and is at position B, and from Earth it appears here relative to the background stars. But as Earth, faster moving Earth, catches up, so to speak, to the outer planet at position C, it now appears that Mars is going backwards in the sky. So A, B, and it appears to go backwards, just like the express train passing the local train. The local train appears to go backwards. And then at time D, the outer planet appears here. And then at time E, they appear to be going, the outer planet appears to be going forward again. So it's a pretty simple explanation for this retrograde motion if you have a sun-centered universe. But in ancient times, they could not accept the sun-centered universe and basically believed that everything orbited Earth, or a location quite close to Earth, and they didn't just orbit around Earth with circular patterns, but they had to use more than just simple circles for the orbits of the 7 planets and the stars of the celestial sphere. And they had to use circles upon circles to generate a geocentric universe with observed retrograde motions. So here is an epicycle on top of a main orbit, a main deferent orbit. So whether this is Mars or Jupiter or any other outer planet, or any planet, an epicycle is fixed on top of the main deferent orbit, and the planet travels on that epicycle in a loop while going around the main deferent orbit. So this made it easy to explain why the planet would, for some portions of its orbit, and from here to here, from Earth's view, the planet would appear to go backwards. So it's going around the main deferent orbit in a counterclockwise fashion. It's going around its epicycle in a counterclockwise fashion. But for this location here until this location here, it appears from Earth that that planet would be going backwards in the sky, and that is the retrograde motion. So they used circles upon circles called epicycles, and they had to be fixed just so to match the observations of the moving planets. But actually, even with circles upon circles, so that this epicycle would have an additional circle upon it, and that epicycle would have an additional loop on it, that even with 80 epicycles, it still didn't quite work according to the precision of the observations of the day. So it's pretty fair to say that astronomy was ready for a revolution of thought by the time the telescope was used in 1610 to discover things in the sky never before seen to the human eye and experience. And these observations, which anyone could take, really dismantled the Earth from its central position in the universe, and really no one has turned back since. And that is our current perspective. And I just want to say that this section 2.3 on astrology and astronomy has certainly many interesting facts in it, but I would say that there are no two astronomers on Earth who would make the same textbook. So there are some things in that are expressed in this section that I think are judgmental unnecessarily, and so I just hope that you take anything that seems amiss with a grain of salt. But in any case, we have table 2.1, and we have the zodiacal constellations depicted here. Certainly there are many versions of these images, but these zodiacal constellations are the ones that appear behind the Earth during different durations of the Earth's orbit around the Sun. And yes, the textbook definitely addresses interesting historical roots of astrology and astronomy, which have a very intertwined history. Actually, astrology, astronomy, and even religion have an intertwined history, but I really won't elaborate beyond this, beyond just making the point that Ophiuchus is actually part of the zodiacal constellations, even though it's not typically depicted in the astrological constellation set, such as the ones in the newspaper. And the other fact that precession causes the constellations behind the sun on your birthday these days to be different than the one that's in the newspaper. The dates that are listed in the newspaper are dates that were set long ago when these associations were first made. So on this topic of astrology and astronomy, I pretty much will only ask that you know that you're taking an astronomy class, and it's not an astrology class. So, how did we get to our present understanding of the universe? Section 2.4 is called The Birth of Modern Astronomy, and this is a picture, or a painting, sorry, of Nicholas Copernicus, and he reintroduced the idea of a heliocentric universe at a time when other thinkers were also very much concerned about the problems in the Ptolemaic model, the geocentric model, the Earth-centered model. They were unsatisfied with this model because it didn't exactly predict the positions of the planets correctly. So there was a period in history where numerous thinkers, Copernicus, Galileo, Tycho Brahe, Kepler, were actively working approximately at the same time, and it led to this revolution of thought that led to our modern accepted understanding today. So I just want to mention that the textbook's cursory treatment of the history of astronomy before Copernicus at the beginning of the section, it's not incorrect, but it also has gaping holes in it. So this is not a history class, though, so I won't make a big point of it, except for people. There's so much about the history of astronomy that people can get their own doctorates in the history of astronomy and still have an incomplete knowledge. So the somewhat cursory history of astronomy in the first section of 2.4 that's delivered might have some flaws to it. We'll focus on the things that are correct, and the things that we will carry with us into the future part of the class. So, with that said, after a period of global strife during Copernicus's time, global strife as well as cultural exchange, Copernicus of Poland reintroduces the idea of a heliocentric universe that placed the sun at the center of the universe, with planets moving in circular orbits around it. So we no longer accept that circular orbits are correct, but that was part of the model that he reintroduced with the sun-centered model. He presented counterpoints to the geocentric, the Earth-centered model, that had dominated for the past 1,500 years, approximately. And so, given that this Ptolemaic Earth-centered model did not predict things correctly, he was motivated to find a new and correct model, a better predicting model. So up until then, and including his arguments, they're all philosophical, meaning that nothing about space and nature was measured. The telescope was not used. His arguments were all philosophical. They're all ideas that the human creates, as opposed to using observations with an instrument like a telescope to make assertions. And his ideas certainly were not accepted in his lifetime. But we ultimately find out that the telescope's observations support a heliocentric very well. So Copernicus got that right. But the tool of math used by the following thinkers shows that he was wrong to use a circular orbit. And what we see here is one of the 4 most important observations with a telescope used by Galileo on the sky to observe things never seen before, and this is showing the observation of the phases of Venus. So he pointed a telescope, which the simplest telescope is 2 lenses, used in conjunction to observe the sky, and he observed the phases of Venus. And these phases were similar to the phases of the moon, but what's groundbreaking about this observation is that these phases are not possible if you have an Earth-centered rather than a sun-centered universe. So as Venus goes around Earth, when it's very far away, the sun illuminates the face of it that is easy for you to see from Earth. But as Venus goes between Earth and the sun, we actually have sight of the shadow side, and when it's right here, it's in the new phase, and we see the entire shadow portion of Venus. And only when it emerges from that position do we get to see the crescent phase, or a larger crescent phase, or a half phase, or the gibbous phase, or in fact a full. This is not possible in a geocentric universe, but it was not possible to even know that Venus exhibits phases without the use of a telescope, such as was done by Galileo, and his telescope was actually quite a simple instrument that he